My name is Nolan Childs. I'm a sophomore undergraduate student at Fordham University studying cell and molecular neuroscience. This presentation will be on my work with Dr. Joshua Schreier of the Department of Chemistry and my work on applying the Drosophila olfactory neural network to drug discovery. A challenge of drug discovery is exploring a vast chemical space for ligand molecules while preserving structural diversity. Current accepted approaches to drug discovery rely on automated high-throughput screening to assess the activity of a large library of molecules against a target of interest. These approaches yield very low successful hit rates because molecules are not filtered in any way before testing for activity. Identifying an approach which optimizes this hit-to-lead ratio would allow for the assessment of a wider variety of compounds by eliminating the need to physically screen for molecules which have been predicted to be inactive. Molecular fingerprints convey structure in the form of a binary string, and one common representation is the Morgan fingerprint. The process of creating a unique molecular fingerprint involves layering different structural features together into one single string. The position of bits in this string conveys specific information about the substructures of that compound. Therefore, molecules with similar substructures will encode fingerprints with similar bits. So for example, in this image to the left here, the phenol, amino, and carboxyl groups all correspond to a specific point in the binary string of that molecule. Existing machine learning methods using molecular fingerprints require large data sets which are not always available in experimental settings. In an area of limited data, such as drug discovery, a model which remains functional under restricted data conditions provides obvious benefits. Biological neural networks present a possible solution to this problem. Drosophila use a neural network to detect and memorize odors as they explore their environment. Odors are stored in the fruit fly memory essentially as the sum totals of the most active receptor neuron firing rates. When a new odor is encountered, it is evaluated by these same neurons, and a determination is made by specialized output neurons on whether or not the fly has been exposed to this information previously. A locality-sensitive Bloom filter approximates the Drosophila neural circuit. Much like a traditional Bloom filter, training data is processed by a random projection matrix, and the top values in the projected vector are stored at specific positions in the filter. This mimics the fruit fly's ability to evaluate neuron firing rates and assign the collection of most active neurons as the marker for a given odor. This filter, unlike a traditional Bloom filter, also predicts the degree of novelty in the same way that the fruit fly determines the similarity of one odor to previously observed odors. In our application, the proportion of bit overlap between the original filter and a query fingerprint, which has been processed by the system, conveys this information. A proportion near 0 indicates high novelty, and a output that is near 1 indicates high similarity with the training data. Our single filter system prediction accuracy is significant. The filter size was set to 2,000 bits with 50 hash functions. Given a data set of known active and inactive molecules towards a target, this filter was trained with 300 fingerprints corresponding to active and only active molecules. 500 different fingerprints from the same data set were then evaluated by the filter, where half were known actives and half were inactives. The resulting outputs were then ranked, and the highest outputs were extracted and predicted to be active. When this extraction was large relative to the number of fingerprints evaluated, accuracy was low at 59%. However, with smaller extracted lists, accuracy greatly improved, indicating that active fingerprints were in fact scored as more similar to the training data than inactives. This one-filter system provides a possible alternative to traditional classification methods. The molecular fingerprint data, which was used to evaluate our filter, was also categorized by 4 common classifier methods, these being the decision tree, random forest, logistic regression, and nearest neighbor classifiers. The logistic regression model performed best on the data that we used at 62.5% accuracy. Our fruit fly-inspired model predicted with superior accuracy for relatively small sampling proportions, peaking at a 5% sampling with an accuracy around 90%. It can be concluded then that this model has real promise in providing an alternative route to pre-screening in drug discovery. However, our model does suffer somewhat in processing speed. Our two-filter system predicts with 56% accuracy. Instead of evaluating all data through one filter trained with active fingerprints, here we created two separate filters, one trained with 100 actives, the other with 100 inactives. Hyperparameters were kept the same as the one-filter system explained previously. Queries are then processed by both filters, and the filter which yields a higher output is determined to contain training data which is more similar to the query. In other words, ideally, active fingerprints should receive a higher output from the filter trained with with actives. These results support the conclusion that our modified Bloom filter can identify structural similarity between molecular fingerprints. The one-filter ranking system shows promise in future applications towards drug discovery, while the two-filter classification system requires further evaluation in order to determine its utility. That is my presentation. Thank you very much.